All right. Good morning, everybody. Class recording started. So just to make sure we're official here. All right. So yesterday we left off on question number 5, and we talked about this swimming pool that needed to be heated. And so whenever we're talking about the temperature of an object changing, we're going to end up using this equation, right? Because that accounts for how much energy we put into that object. That's the Q value. How big is the object? That's the M value. What is its specific heat? That's the C. And then ultimately what the temperature change is, right? This equation works for substances that are in a single state of matter. If we have substances that are changing phase, we have to add in another term, and we'll talk about that later when we get into latent heat. That's one of the questions later on. And so we talked about this swimming pool, and we said that the hardest part of this question, well, maybe not the hardest part, but a hard part of this question is, it says, estimate the cost of heating the water in a typical swimming pool from 5 degrees Celsius to a suitable temperature for swimming. 4 of the points on this problem, right, we talked about, is just coming up with dimensions of the swimming pool and how warm we want to make it, right? So I told you I got these values straight from the book, the answer key in the book, and that's where my dimension of the swimming pool came from. 20 meters long, 5 meters wide, 2 meters deep, and a temperature of 25 degrees Celsius. That could be difficult because you may not even know what the typical temperature of a swimming pool is, but if you come up with something, right? And so the other thing, that's right. It's not, we're not normal school procedures right here. So the other thing that we talked about is the cost per kilowatt hour is 10 cents. And so we just kind of interpreted what a kilowatt hour is, right? A kilowatt is 1,000 watts, and that's 1,000 joules per second. For an hour, 3,600 seconds, a kilowatt hour corresponds to 3.6 times 10 to the 6 joules worth of energy. So once we figured out the dimensions of the swimming pool, we figured out the volume of the swimming pool, then using the density, we figured out the mass of the water that was in the swimming pool. We got that value there. It told us in the problem what the specific heat capacity for water is. That's why we got that there. And then, assuming that our typical swimming pool temperature was 25 degrees Celsius, looking at the change in temperature from 5 to 25, that's an increase of 20. So we figured out that it would take this many joules to heat the swimming pool. But in this problem, it didn't ask us for the number of joules, it asked us for the cost. So, knowing that we needed this many joules to heat the swimming pool, each kilowatt hour relates to this many joules. We divided this by this and got that it would take 4639 kilowatt hours to heat the swimming pool at a cost of 10 cents a piece. That got us to $464. Good there? All right, the second part of this problem, so it says in winter, I'm about the same setup, it says an electrical heater for swimming pools has the following information written on its side, 50 hertz and 2.3 kilowatts. It says estimate how many days it would take this heater to heat the water in the swimming pool. All right? So we knew from the previous section that, or from the previous problem, that this is the number of kilowatt hours that it takes to heat the swimming pool to that temperature, right? 4639. So we know that this is how many kilowatt hours we're going to need. It tells us that the heater, right, only has a power rating of 2.3 kilowatt hours. Right? Even though it says kilowatts, that's what it is, right? And so, real simple, we're just going to divide the number of kilowatt hours that we need divided by the number of kilowatts that the heater can supply. kilowatts cancel, the only unit that we have left is what? Hours, and that's good, right? Because this question is asking us not necessarily for hours, but it is asking us for a time, right? How many days? Oh, it's a lot of days. Yep. It's 2.3 kilowatts is not a very strong heater, obviously, you know. So 2000 and what was it? 16 or 2017? You did 16.9. And that's hours, right? But it didn't ask us for hours, it asked us for days, right? So we're going to divide that by 24, and we're going to get approximately 84 days. Winter's basically over now, right? So, right, obviously that heater, like I said, it's not a very high wattage heater, right? But that's how long it will take with that heater. For part BII, we actually kind of talked about this a little bit yesterday at the end of class, right? We're assuming a couple of things. So it says 2 reasons why this can only be an approximation. So what did we assume about this situation? There is no heat lost, right, to outside forces. That the pool Say again. That was previous. That was a previous question. So we talked about that. First, is all of the energy going into the heater being directly translated into heat of the water? We're assuming it is, right? But for the heater to work, what actually has to happen first? It has to heat up, right? So some of that energy is going to heat the heater itself up, then it can transfer that energy into the water, right? And the other thing we talked about is, right, is the swimming pool open to the air? And if it is, what's going to happen to that heated water, right? It's going to lose some of its energy to that air. If it's a windy day, now it's even losing more water or energy to the air, right? So, right, 2 reasons why this can only be approximation. You know, there's a couple different ways we can go with this. One is the fact that we're assuming all the energy that goes into the heater is being directly converted into the water, which is not necessarily true. The heater itself has to heat up a little bit, right? And then the second thing is that we're assuming that once the water gains that energy, it's going to keep it, and that's not the case either. All right, good there? You okay with that? Alright, so number 6. It says a cylinder is fitted with a piston that contains 0.23 moles of helium gas. The following data are available for the helium with the piston in the position shown. It gives you volume, pressure, temperature. It says use the data to calculate the value for the universal gas constant. Alright? Universal gas constant is going to show up in your data booklet. I forgot to pull up the data booklet today. But it is going to be in your data booklet, right? It says, but use the data to calculate a value. So we said yesterday, right, there's 4 things that we can measure about a gas in order to describe it, right? They are what? Those 4 right there, right? Volume, pressure, temperature, and then the number of moles. So we've got those 4 things. And then we said that those 4 things are related to each other through that equation, right, which is our ideal gas law. Okay? R is the universal gas constant in there, so we just rearrange. And now it's just a plug and chug problem. Good. That crazy unit is just there so that whenever we use, this is just the unit, we just mash together all the units. There's some ways we can actually combine those units to get them in a more simpler form, but if you just put all of the units for the measurements they gave you originally, that's fine. Okay? This unit on the gas constant is a crazy unit because if we're using the gas constant to calculate one of the other four things, all the other units have to cancel to leave us with whatever unit we're trying to measure. So that's why all four of the other units have to be there so that they can all cancel and leave the one that we need later on. Okay? All right. Assumption made in the calculation above.
That it's an ideal gas.
An ideal gas, right? And so what are some characteristics of an ideal gas?
Infinite pressure, or they don't touch each other, something like that.
There's perfectly elastic collisions. So when the molecules of the gas either run into each other or into the container, perfectly elastic, no energy is lost. Okay? That's one assumption. What else?
Points.
They're points. They have, the individual particles have no volume. Okay? That could, more so for the ideal gas. Gases themselves generally have a lot of energy, but an ideal gas isn't going to lose any of that energy by running into the walls or running into each other. Okay? No volume of particles, no energy lost. Right?
Is it a direct heat volume relationship?
Direct heat volume relationship. Oh, sorry, no intermolecular forces. That's the other one. So that, yeah, and then Graham, that's what that relationship gets into, right? That if we were to slow down those particles, right, ideally they wouldn't start attracting each other and turn into a liquid, right? That they would remain in the gaseous state, but in reality that doesn't happen. Yeah, so assumptions about an ideal gas: particles have no volume, all collisions are totally elastic, we don't lose any energy, and there's no intermolecular forces. Like those are three biggies. Morning, Fuad. Fuad, we're recording. I just want to let you know as soon as you walk into the room. So if you have any inappropriate memes, maybe hold on to them. Maybe. So. All right. Good there. That's a pretty straightforward one, right? Just ask you to calculate the universal gas constants. Okay. All right. Oh, Fuad, here's the. We're working on this page. I handed it out yesterday, so we're actually on the last problem already. So. All right. So it says. This question is about determining the specific latent heat of fusion of ice, okay? We talked about, at the beginning of today, this equation is great for determining the energy that is, the energy required to either heat something up or cool something down, as long as it's the same state of matter. When we have an object changing phases, the amount of heat it gains or loses is different than when it's in a solid, or when it's in a continuous state or in the same state. All right. So here, when we talk about specific latent heat of fusion, that's the amount of energy that it takes to take a solid and turn it into a liquid, or take a liquid and turn it into a solid, depending on whether we're gaining that energy or losing that energy, right? So it says, and you guys did this experiment in class, whether you remember it or not, it's another thing, but you did, I promise, right? So it says, a student determines the specific latent heat of fusion of ice at home. You guys did it in the classroom instead of doing it at home, but you know. She takes some ice from the freezer, measures its mass, and mixes it with a known mass of water in an insulating jug. She stirs until all the ice has melted and measures the final temperature of the mixture. She also measures the temperature in the freezer and the initial temperature of the water. She records her measurements here as follows. Specific heat capacities of water and ice are given to you below. Okay? All right. Set up an appropriate equation representing energy transfers during the process of coming to thermal equilibrium that will enable her to solve for the latent, or the specific latent heat of ice. Insert values into the equation from the data above, but do not solve the equation. Okay? All right, so whenever we're talking about energy transfers to heat up substances, what assumption do we make?
Nothing's lost.
Nothing is lost, right? We have total energy conservation. Okay? So, going back, there are actually 4 energy transfers that occur here. Okay? What has to happen to bring this ice-water mixture into equilibrium? 4 things have to happen.
Starting when?
From the time she puts the solid ice into the liquid water. Okay, so this is where we have a cup.
Oh, it's heating down.
Okay, so
And it
what's
changes,
one,
and
what's,
goes either.
there's 4 things that have to happen energy-wise in order to bring this mixture to thermal equilibrium. Thermal equilibrium means what, Fuad? Same temperature, right? So 4 things have to happen, okay? All right, so let's talk about the water that's already in the cup. What does the water that's in the cup have to do?
So it's gonna cool.
It's going to cool down, so it's going to lose energy. That's one energy transfer that has to occur, okay?
It's gonna melt. So that's the like
So that's 2, but what has to happen to the ice before it melts?
phase.
That's melting. What has to happen to the ice before it melts?
Reach equilibrium.
What is the initial temperature of the ice? It has to heat up 12 degrees. That's a 3rd energy transfer. So that's, now we're down to 3, right? What else has to happen? That's the latent heat part.
So
Yep.
then it heats back up.
Then
to
it,
that.
then it heats
to the
back
water.
up to 15, right? So 4 things have to happen. The ice solid form has to warm up to 0. At 0, the ice has to melt. Then the melted ice has to heat up from 0 to 15. Those 3 energy transfers have to occur, and then the water that's in the cup has to cool down from 22 to 15. Does that make sense? So 4 energy transfers. At the end of the day, how much energy does there have to be in this entire system? Same as we started with, right? So all of these energy changes that occur all have to add up to what? All the energy changes that occur have to add up to what? 0. Because we have to have the same amount of energy at the end as we do at the beginning. Does that make sense? Okay. So 0 equals. Okay. So first, we have Q for the ice. Okay. Ice heating up from -12 to 0. Right? Then we have Q for melting ice. That's a phase change. Okay? Then we have Q for ice. How do I want to say this? I don't know how I want to use subscripts, but let's do this. Let's call the ice 1, and let's call the water 2. Okay? So, we know at the end of the day, everything has to add up to 0. So first, we have the heat that ice, number 1, gains in the solid phase. That's the S. Okay? Then, the heat that the ice gains while it's melting. Okay? Good there? Then, that heat that it has to continue to gain to go from 0 degrees Celsius up to 15 degrees Celsius, plus the heat that the water already in the cup has to lose, but it's still always going to be a liquid. Okay? Does that make sense so far? Okay. All right. So here's where this problem gets a little, well, this is the tricky part of the problem, right? This, and this all relate to a substance in a single state of matter. And we said, whenever we have a substance in a single state of matter, we can use that equation. Okay? But this one involves a substance changing state. What do we know about the temperature while a substance is changing state? It's constant, right? So we can't use this equation, because what is delta T if the temperature is constant? 0, right? So we can't use that equation for a substance that is changing state. When we have a substance that is changing state, the heat of fusion is equal to the mass of whatever we're talking about times the latent heat of fusion. That's L. Okay? So we take the mass times L, which is a known value. And in this case here, that will enable her to solve for the specific latent heat, Li, of the ice. That's what it's asking us to solve for. Okay? Good there? Okay so far? All right. Insert values into the equation from the data above, but do not solve the equation. Okay? For all the purple check marks, right? It's MC delta T. For this, it's going to be M times the latent heat of fusion. Okay? At the end of the day, everything's got to be 0. Okay? So, now we start plugging in things we know, right? Okay? There are 4 M's in this equation. What do we know about 3 of them? They're the same, right? Because they deal with this, right? So, this M, and this M are all going to be 0.12. Does that make sense? Even when it goes from a solid phase to a liquid phase, its mass doesn't change. Okay? All right. There are 3 C's in this equation. All right? That's the specific heat of ice. Yes? Okay. And then this one and this one are going to be the specific heat of water. Even though this third term, right, that's the ice after it melted, but after it melted, now it's water, so it has the specific heat of water, not the specific heat of ice anymore. Okay? There's 3 delta T's in this equation. Okay? This delta T, positive 12. Do you understand where that came from? You okay with that? That one's positive 12, right? This delta T is positive 15. You okay with that flow?
Okay.
Okay. going, well, in order to get the ice to melt, it has to be what temperature? 0 Celsius, right? Whenever we're doing delta something, it's always final minus initial, right? So the final temperature for this delta T is 0, because that's the ice heating up, and then minus 12, right? Yeah. Even though it's warming up, so delta T has to be positive, even though we started in the negative numbers, the change is positive, right? Does that make sense? And then this delta T is going to be -7. Okay? And then finally, right, here, right, that mass is that mass right there, except the mass of the water. Okay? Because this one is cooling down while the rest of them are heating up, we have positive terms and a negative term, and that's why we can end up at 0. Right? Good there? Does that make sense?
Does it want us to rearrange that?
You could, I suppose, right? All it says is set up an appropriate equation representing the energy transfers. So I guess, you could set it up to equal L, but that equation would give you enough to solve for L. Now it's just a matter of algebra and getting where it needs to go to. All right, good there? Get that? All right. All right. Part B. Explain the physical meaning of each energy transfer term in your equation, but not each symbol. All right? These are energy transfer terms, right? What did we say this one represents?
Heating up of the ice.
Heating up of the ice. Melting of the ice. Heating up of the melted ice, right? And then this is the, what is it? It's cooling down the water that was already in the cup, right? That's part B. Explain what your energy terms mean. Or explain, right? What does it say? It says explain the physical meaning of each energy transfer, but not each symbol, right? So they don't want you to say, this is the latent heat of fusion, and this is the energy that, right, explain what it means. This is the energy needed to increase, or to warm up the ice to melting temperature. This is the energy needed to melt the ice. This is the energy needed to heat the melted ice up to the equilibrium temperature. This is the energy lost by the water to get it to the equilibrium temperature. Okay. Good there? State an assumption you have made about the experiment and setting up your equation in A. What's the first assumption that we made? Conservation, right? That there's no only energy gained by the ice is going to be lost by the water, and that's it, right? Nothing else there. And that shows up in our equation by setting everything equal to 0, right? That we have to end up with the same amount of energy at the beginning as we did at the end. You there? Why should she take the temperature of the mixture immediately after the ice has melted? Loses heat to the outside the longer it sits there, right? Okay. Conceptual question. From a microscopic point of view, in terms of molecular behavior, why the temperature of the ice does not increase when it is melting. Okay? So there are 2 types of energy we associate with molecules, kinetic and potential. Right? Kinetic energy manifests itself in what? Temperature. But here the temperature isn't changing. Right? So that means that the energy that we're putting into these molecules has to be going into what? Potential energy, right? Those intermolecular forces have to be broken apart to take it from the solid phase to the liquid phase. Does that make sense when I word it that way, right? Right? In the solid phase, there are very pretty strong intermolecular forces holding all of those molecules in place. But in the liquid phase, they have much more freedom to move. We got to break those intermolecular forces so that they have the freedom to move. That happens by going into or decreasing the potential energy of the intermolecular forces before we can start increasing the kinetic energy of the molecules again.
So you're heating like a block of ice.
Okay.
You're adding energy to it,
Okay.
but you're decreasing the potential energy.
Not yet. The potential energy changes only occur during phase changes. Okay.
So all the kinetic energy potential?
No. So in ice, okay, those objects are in a fixed position, but not stationary, right? There's that vibratory motion that goes along with it. As you heat up a block of ice, the vibratory motion gets faster and faster and faster, but they're still in their fixed positions. So you're increasing the kinetic energy because those molecules are vibrating more as you heat up the block of ice. Does that make sense?
Yeah.
But they're still in their fixed positions. To get them out of their fixed positions, you have to separate them against the intermolecular forces that are holding them in places. Does that make sense? That doesn't result necessarily in more translational motion, but because you're breaking the, like, bonds is strong, they're not bonded together, but they are like attracted to each
It's
other.
like you can only reach a certain point for it to get solid.
Right.
It has to like break apart.
Right. Yeah, like they can only vibrate in place so much before they have to get out of that arrangement, right? Getting out of that arrangement, that's the latent heat of fusion that breaks the arrangement up. Now, once the arrangement is broken, they can move more, and that's
So
when...
it takes energy to break the.
Yes,
Okay.
because technically you're doing work because you are working against a force. That force is an intermolecular force, but it's still a force. So yeah, it's work, and that's why it takes energy to separate those molecules. How's that? Good there? Okay. All right. Let's pause here a second.
Perfect. When I tried.
Glad we got that on recording. That's good. All right, we're back. So next section, chapter 4, is about waves and characteristics of waves and then wave behavior. So we'll start with that a little bit. Like I said, I didn't give you guys the rundown. I didn't give you the information, but I'll get that to you sometime later today. So we'll start this page here, and then we'll finish it in our half an hour that we have later on, because there's nothing like having double physics sessions on the same day. Good time. Good time. All right. A surfer is out beyond the breaking surf in a deep water region where the ocean waves are sinusoidal in shape. The crests are 20 meters apart, and the surfer rises a vertical distance of 4 meters from wave trough to crest in a time of 2 seconds. What is the speed of the waves? All right. Probably best thing here is to draw us a picture, all right? Okay.
Whoa. That's nice. Yeah, that'd be good. Steady ball.
Oh, it's 20 plus 5.
C equals lambda.
Don't make it that. Don't even make it that tough. All right.
Speed of light.
Oh, you're right on that. So sorry. That's the speed of any wave, right? So speed for any wave, we can do 2 ways. We can either go lambda f. Lambda is wavelength and f is frequency. We can also calculate this way, right? Where t is the period. All right. So in this case, it says crests are 20 meters apart. That's giving you the what? The distance from crest to crest is the wavelength, right? So that's going to be 20 meters. Okay? But then, this is where it gets a little bit tricky, right? It says, the surfer rises a vertical distance of 4 meters from wave trough to crest. If we're talking about rising or falling, what property of the wave are we talking about? That's amplitude, right? Now, in this case, though, if it says 4 meters from wave trough to crest, the amplitude is actually only what? 2, right? So it's going to be 2 here and 2 here, even though it might not look like that from the drawing, right? Okay. But does that have any bearing on our speed? It doesn't, but this part does. Trough to crest in a time of 2 seconds, okay? Trough to crest is only how much of a wave? It's only half of a wave, right? But in this case, the period is the time for a full wave. Does that make sense? Okay. So we don't know the frequency here, but we do know that half a wave.
Pardon the interruption. Any student that is still testing, we still have over a half hour of testing time left, so we will transfer your test. Please follow these directions if you're still testing, and we will transfer your test. So if you're still testing, press pause on your test, pick up your test ticket, and go to room A125. Teachers, please do not stop your test session until we have logged them onto their new test session. Okay, again, any student that needs to continue testing, pick up your test ticket, pause your current test, and walk on down to room A125, the library lab, A125. Thank you.
Does that make sense? All the writing that I did there. So our speed of our wave is going to be 5 meters per second. Okay. Speed is, there's 2 ways we can calculate speed. We can go wavelength times frequency, or we can go wavelength over period. Both of those will get you speed. Okay. Good? Standing waves established in air in a pipe with one closed end and one open end. Air molecules at X, all right? So, standing wave, right? A standing wave is a repeating pattern of constructive interference and destructive interference. Bigger amplitudes and smaller amplitudes, right? Right? So, X is a spot of what? It's a node, and that means what's going on there? Nothing, or destructive interference is going on there. In terms of the air molecules in the medium, what are they doing? Resting, nothing, right? Okay. A compression or a rarefaction is an area of higher density or lower density, but those only happen when we have interference patterns going on, right?
Compression of higher density?
Say again? Yeah, compression's higher density, rarefaction is lower density, but in this spot right here, because it's a node, there is not higher density or lower density, it's just exactly the same density as it was before.
If I was at the bottom of the wave, would be rarefaction?
This?
Yeah.
That's a hard one to tell because antinodes, the greater one, the greater
Oh, if they were combining and then maybe people.
right. That could be 2 compressions adding up together, or it could be 2 rarefactions adding up together. They would sort of both look the same. Does that make sense? Okay. So that's a hard one to tell. But at the node, where there is no compression or rarefaction, it's just sitting there. Right. It's not at a center of compression or rarefaction because the medium is not disturbed at that point. Good there? All right. Let's end on this question because it's pretty easy, and then we'll pick it up later on. Okay? This question is about sound waves. First, what kind of waves are sound waves? They're longitudinal. Okay. So it says a sound wave frequency 660 hertz passes through air. The vibration of a particle displacement with distance along the wave at one instant of time is shown below. That's like, okay? This is how far away from equilibrium are we. This is how far is the wave travel. right? State whether the wave is an example of longitudinal or transverse. If it's a sound wave, it's gotta be what? It's longitudinal. You can't necessarily tell that from the picture, right? But because they told you it was a sound wave, it has to be longitudinal, okay? Using the data from the above graph, deduce this for the sound wave, right? So, wavelength, right? That's one wave, yes? What's the distance that we've covered there? Half a meter. And notice, right? These are only 1-point questions. They're just looking for answers, right? They're just looking for amplitude. Amplitude's gonna be what? Half a millimeter. 0.5 millimeters. So the amplitude is this distance from there to there. Yeah, keep in mind that the units are different on the x-axis and the y-axis. Alright, then speed. We said there's 2 ways that we can calculate speed, right? Even though it didn't ask you about it and you can't tell about it from this graph, what information did they give you about this sound wave in the information leading up to it? They gave you the frequency right here, right? In part B1, you figured out the wavelength. So speed is frequency times wavelength. And right, that should give you that. How's that? Good there? Alright. Let's pause for now and we'll bring it back here in an hour and a half or so.